Okay, so in this video, we're looking at the final part of our series here of hyperbolic functions, and we're going to focus on integrating them. So, and really, we're just going to focus on integrating functions that have the hyperbolic trig in them. I do present the antiderivatives of things that will result in the inverse functions, but I don't think there's anything like that in our homework. So we'll focus on just these. I think there's 4 examples, and honestly, they really mimic what we first learned in U substitution when we looked at trig. So like for that first example, maybe there. Okay, good. So the first example, like our U is going to be what's inside our hyperbolic cosine function. So let's let U equal root x. Its derivative then would be 1 over 2 root x. Well, my smartboard is my smartboard's not responding as quickly. There we go. And so then we're just off by a factor of 2. So then it becomes a really nice substitution here. And actually, I think these are even easier than just normal trig, because we don't have to worry about which one was negative, which one is positive in that direction with sines and cosines. Integral and derivative of cosh is still going to be sinh regardless, right? So this is just 2 sinh plus c, and then that becomes 2 sinh of the square root of x plus c. Okay. Sorry that I feel like there's a delay from when I write to what's responding on here. So hopefully that won't impede the video too much. So let's go to the next example then. So the next example, hyperbolic tangent. And just like when we first learned how to integrate normal tangent, let's rewrite that as a quotient. So that's sinh. It's a sinh, right? That joke never gets old, right? Sinh over cosh. And we let our u, I guess these are still x's, my bad. I got ahead of myself, make those x's. So our u will be our denominator. So u is equal to cosh. Its derivative, again, it's a sinh. We don't need to worry about any negatives. So it becomes a really nice integral, just 1 over u du, which is the natural log of absolute value of u plus c. Now, technically, we don't really need absolute value because the hyperbolic cosine function is already positive, right? Think about what is it? What is the hyperbolic cosine made of, right? Remember, it's defined to be e to the x, which is positive, e to the negative x, which is still positive, and then divide by 2. So we don't really need absolute value, but it's okay. Leave it. Okay, and then next one, just hopefully again recognizing that that's within hyperbolic secant squared, so that becomes our u. Its derivative is pretty much sitting right outside that function, just off by a factor of 1/3. So then when we integrate this, 1/3 hyperbolic secant squared of u, and again, this integral should be familiar from when we just did normal trig, because just like normal trig, secant squared's tangent's derivative. So hyperbolic secant squared actually is also hyperbolic tangent. So that's one of them that doesn't change from our trig that we know based on the unit circle, right? So then, oops, I said it and I just didn't write it. Let's try that again. 1/3 tangent. There it is. 1/3 hyperbolic tangent of u plus c. And then, of course, our u value was x cubed. I'm like always just double checking to make sure I'm writing that h right for that hyperbolic function. I'm sure in one of these videos I forgot, so I apologize. And then our last example here, wow, right? We got a lot of trig going on here, right? Sinh of tangent theta times secant squared theta, but honestly, it's a nice u substitution with u being tangent. It's going to actually get rid of a lot of things because its derivative is secant squared. So maybe it looked intimidating, but actually it's a really nice, it's a really, really nice substitution. So we've got the sinh of u, and let's go ahead and change our bounds. Tangent of pi over 4 is 1. And then for a 30-degree angle, which is pi over 6, remember our tangent is 1 over root 3. So then our antiderivative of sinh is cosh. We could leave it in terms of u because we've already changed our bounds, right? U is 1 over root 3 to 1. And then, depending on, what it's asking, there's no reason why we can't just leave it like this. Cosh of 1 minus cosh of 1 over root 3. But again, if you wanted to really give it in terms of an exponential function, you could, right? E to the x minus e to the x plus e to the negative x over 2 is hyperbolic cosine. And I think that's it. The last piece just kind of says, here if you have functions that are of this format, they would result in basically the inverse hyperbolic trig functions. Like this should look really, really familiar to you, right? Because that's the that's hyperbolic sine. And then this one again should look familiar to you if you go back, because that's hyperbolic tangent, and then this one here would be hyperbolic secant. So if you are integrating things that start in this structure over here, it certainly looks like could be trig substitution, similar to that with the characteristic structure of our squares, but slightly different. And then you would use one of your inverse hyperbolic trig functions as its integral. But the homework that you're going to do for this problem set does not involve any of those, I believe. So I think you should be okay. And if I'll double check that, but really just knowing how to integrate your basic hyperbolic trig functions, and you should see a mirror image, or a mirror similarity, I guess is the word I'm looking for, between what we do in normal trig and then what you see in what these examples in your homework.